Good day, folks. I'd like to show you today maybe something that could be useful. It's a crude but interesting way to test your water for basically metallic and ion and various impurities, in other words. So basically tap water, even town water, could be far from perfect water. So what's very interesting, by the way, of water is if it were 100% filtered, so in other words pure H2O is 100% non-conductive. So it's actually a perfect insulator, which means it could actually be suitable for a dielectric as well. So you could actually use water capacitors if you can build them with pure water. It's actually a pretty good dielectric. So with that said, and some of the experiments with power cells, back to the very basic galvanic power cell, I had an idea. So I am going to show you something very interesting. So here I'm going to show you a voltmeter, a very basic voltmeter here, so bear with me. So here's the voltmeter sitting on my table, set to 2 volts right now, DC. So we're going to make sure the meter works. So it should read 0 when I touch it there, so sure thing. When I hold the 2 together here, I get 0, which it should be doing, just showing you that the meter is not doing anything weird. So what we're going to do, we're going to head over to the kitchen here, and I'm going to grab a regular cup of tap water. We'll see how good it is. So just filling it up directly with nothing special, with just tap water. Alright, that looks pretty good. So we're just going to head over back to the table here. Now essentially the idea is if there's anything like iron and anything that shouldn't be in there, and there's basically a galvanic action, so in other words different minerals and metals essentially forming a traditional microgalvanic cells, and the water itself along with its other impurities acting as a very weak electric conductor to those cells. So what I'm getting at is swooshing the water around here, you're going to end up with random, if it's not pure, random series configuration. So depending where you put your probes here, so which is very interesting, 2 of the same metals, okay? So the 2 probes here. So what I'm getting at is it's a microgalvanic action, but not with the probes. The probes are just acting as conductors through the water getting to the nearest series cell. So this could always change by the way the water is. So you'll notice a fluctuating voltage, and it could even sway the other way if the random series cell has if the potential goes more plus or more minus depending on how those series cells forms. So I'm going to put those 2 probes in there now, and look what's going to happen to the meter. See how it jumped, but it goes all over the place because I'm moving the meter around in the water here. So it's random, but my water is basically very impure. And depending where I put it, it may even jump to the negative sometimes. Don't know if I can get it here. Depending where I put it, it could go into the, I'm trying to, maybe I did there, but usually when you mix the water around, you get different readings, see? Because it's all the impurities forming microgalvanic. And the more I mix, sometimes I'd like to show you the negative sign, but if I can't, I can, just because I'm trying to make the video. Oh, I won 0 there. But if I let it still, oh, back up there, I move it a little bit, very erratic, but the point is, microgalvanic cells in here creating a potential difference. So what's very interesting is, again, like I say, this is a very interesting way to quickly test your water. And what does that mean is if this really is at the nanoscale level, even a glass of water would probably have a field, because there's still these galvanic actions at the electrostatic quantum still going on in this cup of water. So essentially, as long as you've got quote-unquote dirty water, it should probably emit a field of its own, but probably because it's such at the nanoscale, so little here that even the ambient noise, if you were to put a coil around here, you wouldn't be able to measure it. But that got me thinking, and I will talk to you about this in a moment here. So what I'm going to get at is basically after I did that experiment on my own, it got me thinking a bit about one of the episodes from Energy from the Vacuum that the Bedini worked on, especially the one where there was this professor from a university, I think, and at the time, this was nearly 20 years ago now, folks, and he was boasting about some system, but he wanted to do something at the nanoscale where you need precise semiconductor technology to build it. And at the time, they were just getting there, maybe a few years, and they were going to have it. And he was proud of this because it essentially worked with the concept where you essentially have NP junctions, and he's using thermal reactions. But probably what came out of their thermal pads today we use for the thermal heat pads, maybe it's a reminiscence of that technology. But needless to say, he was working on a system that he said that at the nanoscale, essentially you could move a single dielectric particle up and down and build nanobot motors and generators, essentially, and stack all that power up coherently and basically extract massive amounts of watts from the ambient heat. Now, one of the issues he had would be instantaneous cooling to essentially absolute zero if he built one the size of a table. So his suggestion was to build one like the size of a school blackboard to dissipate it so that it would just be a minimal cooling, essentially. So it was a good idea. The thing with that is I think you may be trying to reinvent the wheel, because when I was thinking about it, I was thinking, you know, he's going after heat, trying to convert something and then get obviously cold out of it. Now I was thinking, you know, with what I did, the experiment with the water, it seems like just about any water, as long as it's not overly purified, is going to have minerals and irons and all that. So what I'm getting at is at the nanoscale, there's actually quite a lot of galvanic cells that are there no matter what, whether you use them or not, and they're doing their thing, and they're closed loop through the very high impedance of the water, which creates a path through its other impurities that makes it partially conductive and ionic and everything else. So what I'm getting at is at the nanoscale, if you were able to, which is really weird because this means now that if they were doing that or getting ready to do that nearly 20 years ago, folks, it means that for about 20 years now, as far as nanotech manufacturing, nanoscale semiconductors, if you had a setup, you could build this by now. So for 20 years, what I'm getting at is you'd build something like essentially a lattice or a hybrid dielectric at the nanoscale. It could be, there's a few possibilities here, but the thing is you want to interact with the field so that essentially your dielectrics at the nanoscale become your micromotors and generators. You could either make those generate fields with micro antennas or interact through micro nanoscale diode rectifiers and accumulate that field. But the thing is, at the nanoscale, if you can build such a semiconductor, for example here, like it's quite remarkable because, like, say, a typical glass of water, which would have maybe 250 ml of water. So if you'd have something, let's say, a capacitor like semiconductor, but instead of a dielectric, it's got a little tap on there where you just add regular water, and that's what activates your plus and minus, essentially, because you had the factory to build this nanoscale kind of semiconductor. It's a lot, because if you were to calculate it, in theory, you could have hundreds and hundreds of watts of usable power at that scale, a cup of water, if you build the right, essentially, nanoscale tech to interact with those fields that are already there, whether you use them or not. You just need to put the, and now you know it's been 20 years, so don't tell me we don't have the technology. They may not be talking about this, which is really weird because they're talking about AI and everything where they need nuclear power and all that. And they're the semiconductor manufacturers. Don't they know they could just take tap water out of their town and build a semiconductor capacitor-like device, and that thing will put out like hundreds and hundreds of watts for, you know, maybe months? But again, I guess they would want to tell us that you could essentially run your life on water if they would essentially magnet. All it is, it's not even a theory at this point. It's about being able to manufacture it and making a product for the public general usage. So maybe the military knows about this or something, but it's right there in water, whether you use it or not. There's a micro nanoscale galvanic process, unless, of course, you would have pure deionized water filtered that has nothing else but H2O. Then it becomes a perfect insulator. It's It's not a electrolyte. There's no ionic, nothing. But not everyone has that kind of water. Essentially, it doesn't have to be that pure to be considered good for us to drink. So that's why there's a lot of those impurities just in tap water. Can you imagine hundreds of watts in tap water, a cup of it? Can run your heater in theory if you had the right semiconductor material to interact with those fields and rectify them. I mean, it's ridiculous, but that's what it is. Thank mainstream science for that and politics, I guess. So just thought I'd put it out there, folks. You could even research this for yourself if you want to. And with that said, have yourselves all a great day, and always looking forward to your thoughts and your comments and your suggestions. Have yourselves